Hereby, sure, the second part of the lecture, we are looking at single electron transistor. Electrons go between two leads through the island. The transport can be blocked, or it could be as peculiar as I described. Electrons can go one by one. Let us look at it in more detail. Let me talk about Coulomb diamonds. Well, in many languages, diamonds are associated with some precious stones. Well, not in English. In English, diamond means what we call rhomb. So there is no association with precious stones. Very good. What we are going to do is to take a certain n, for instance 0, and figure out at which conditions we have this Coulomb blockade. We will be working in the plane of two voltages. One is transport voltage applied between the leads. Another one is a gate voltage. I express it in terms of induced charge. The charge induced by gate voltage to the island. So C gate, D gate it is. Right. All energy differences, as I said, are linear functions, which means each condition is presented by a line. I have 4 transfers. I have 4 conditions to fulfill. I have 4 lines for different transfers. And I create a room, a diamond in this plane. Right? So in this region of voltage, gate voltage plane, we expect no electron transfers, Coulomb blockade. Fine. What will happen if we take n equals 1? Applying gate voltage, we always shift everything by corresponding amount. So a diamond corresponding to n equals 1 just comes shifted into this position, and -1 comes shifted to here. So we have a periodic structure of diamonds, very typical for any device, any quantum transport system exhibiting Coulomb blockade. Let me show this diamonds in full glory. So the current is absent in these white regions of the plane. Right, and this is illustrated by a plot called a bar. So the current is really 0, about 0 in this region. Then it increases. A question to you: this picture, is it experimental or theoretical? Oh. Is a big chance it is a theoretical picture. It looks too nice to represent the actual experimental data. Fine. Sir, we have Coulomb diamonds. It's a bit boring. In these diamonds, we don't expect any flow of electric current, at least at vanishing temperature. Temperature which is much smaller than Coulomb blockade energy. Let us look at transport. Suppose there are some transfers which can happen. Let me outline a tool with which we can describe the transport. And that's quite universal tool in many fields of physics and many fields of science or practical activity. If you look, for instance, at finance, at stochastic changes at stock markets, most likely you would use the same equation, master equation. Sir, my story would not come in vain. Let us see how I apply master equation in this particular situation. The island, and we have now at the moment single island, can be in states which are characterized by number of charges. Classically, it means basically nothing. Since we're in quantum transport, we apply a rather important thing. It means that quantum coherence between different states is lost. Why is it true? Because eventually there are very many states in each island representing the same charge configuration. There is no gap in all metal with respect to, say, electron-hole excitations with small energy. This gap is present in superconductors. It will be different in superconductors. The states with different charge can be made coherent, but let's postpone it. Let's talk about normal metals. And in this case, there is no quantum coherence between the states with different number of charges. Okay, then different tunnel processes happen, and they're stochastic, and we don't know precisely when we find our system, our island in the state N. We can only know probabilities to find it. Well, these probabilities obey master equation, which is nothing but bookkeeping equation for probability. Perhaps you have heard about this. Let me remind how it is organized on an example of our system, singleton transistor. Let us consider change of probability. Perhaps you can do. Let us see. Let us consider the change of probability to be in a certain state, and this probability will be reduced if there is a possibility to go to all other states, to go from or to the island at a given n. So it's kind of decay of probability with the rates of these processes. So negative processes are positive processes. Income terms. What are income? Initially, the system can be in a state n-1. and electron can come. Or it could be in a status n plus minus 1. An electron with a certain rate can go out. These rates will depend on corresponding initial states. So we have income terms, we have outgoing terms, and if we talk about stationary conditions, about stationary probability, well, we need to have a balance between income and expense, between positive and negative terms. Right? Here just put the rates which I use for the total probability. It doesn't matter from which junction or to which lead does it go, left or right. So it's just a sum over partial rates I've been talking about. Good. Master equation. If we know the rates, and we will know the rates very soon, we can solve it. How to compute current? Because our goal is quantum transport, we want to compute the current. Current in stationary case must be the same for left junction, right junction. Well, if we know the probabilities, we can get the currents very quickly. Again, doing some bookkeeping of the rates. Let us look at the left junction. There's some probability for a system to be in the state n, and in this state we have the rates that contribute to the current with plus sign. We have transfer from the left, transfer with opposite direction to left will come with minus sign. Everything is logical, and we sum up overall possible ends. The same we do with current through the right junction. Well, if we compare these two expressions, it doesn't look like we really have this condition. Is there something wrong? Does our calculation satisfy foolproof rules? Well, it does. The point, it won't be, these currents won't be the same for arbitrary probabilities. But if the probability is a solution of master equation with the same rate, it will certainly hold. Fine. Good. So we can evaluate average current. And okay, let me just mention that it's not really instant current. If one considers timeline of electron transfers, then the current will come in spikes corresponding to these transfers. And what we do, we look at the average of the spikes, over these spikes over sufficiently long time interval. In simple words, we look at DC component of this current. Fine. Now we know how to evaluate current from the master equation. Master equation contains tunnel rates. I want to say more about tunnel rates. Tunneling in metals Let me first describe the case of without interaction, without Coulomb blockade. Then we can get Coulomb blockade with a small step. Let us see, tunnel barrier that we know about. Electrons come to a barrier, they have very little change to get through. Mostly they are reflected. That's the realization of the barrier. There is metallic electrode, for instance, aluminum. That's another lecture. And there is aluminum oxide. Separating these electrodes. Aluminum is very nice material in this respect because oxide and aluminum stops. It doesn't develop always, like for instance in most metals. So aluminum barriers are indeed very thin and very suitable for realization of practical tunnel junctions. Good. So let us see how to get tunnel current. Left lead, right lead. Here the states are occupied up to this level. We apply voltage difference. On the right, the states are occupied up to lower level. What does it mean? In this case, we can have electron transfers within the energy strip EV. Right. We know the current. Just by definition of tunnel conductance, the current is proportional to voltage. How to find the rate? The rate is current divided by number of processes which happen, by number of electron transfers. So we can express the rate in terms of conductance of the barrier and voltage. This voltage difference one associates with the width of the strip available for channeling. The wider the strip, the more transfers we have. Good. Let us modify it for the presence of charging energy, and it appears to be very simple task. Let us see again the same situation. Here electrons are occupied up to this level. This energy strip seems to be available for channeling. Without Coulomb blockade, electrons would go at the same energy. But if there is Coulomb blockade, they charge the island where they go. They charge the island where they go. They have to pay energy, and the only energy which they have in their disposal is kinetic energy. Which means that electron should go at less energy. And that reduces the width of energy strip available for tunneling. So that's how the rates are affected by Coulomb blockade. The energy difference comes into play. One can say, in general, that the rate is proportional to the energy difference because it is associated with the width of energy strip available for channeling. So that gives me the notion of timing rates. They are functions of corresponding energy change. One can also derive the same with the Fermi-Golden rule. Here we have number of electrons which are present at energy E. They have to go to empty spaces at energy E prime, and the difference of their energies is set by Coulomb blockade and voltage applied to the structure. Right, one can do it at final temperature. Let us see. Let us first look at the cold situation. No energy difference. Okay, then the rate exists at negative energy only. If it gets hotter, I have also transfers at positive energy, because in this case energy can come from thermal fluctuations, and generally the rates at final temperatures are bigger. Good. We know all about tunnel rates. We can go to exams. There's something with my computer. I have to check it. Right. Supply is almost good. Need to connect it. So it's about. Should work now. Let me look at manifestations of Coulomb blockade transport. First, also it was the first feature which has been revealed experimentally. It's a phenomenon called Coulomb oscillation. In this case, the actual measurement we do is very simple. We just measure conductance of the structure at low voltage, linear conductance. And we measure it as a function of gate voltage. Then, what one sees is a picture of conductance peaks. Why is it so? Conductance is zero in these domains because we are within the diamond. When we come to the point when two diamonds cross, the energy we have to pay to overcome Coulomb blockade becomes very small. And we can do this with the voltage available. We need to compare the small energy with the temperature we have. So this is eventually set by temperature. Good. So if temperature is lower than Coulomb blockade energy, we have a series of conductance peaks. But what would be this conductance? Can you give me an idea, please? Or let me formulate it in more emotional manner. Suppose you have a friend, experimentalist, which brings you this cave and tells you that this is manifestation of Coulomb blockade oscillations. You look at the units at this axis and understand that conductance is a reverse of 1 ohm. Would you believe this right? No, that's not okay. We remember that isolation is required, good isolation is required for Coulomb blockade. So this conductance has to be smaller than conductance quantum. Inverse of 1 ohm does work. It has to be many orders of magnitude lower. Fine. Periodic peaks. Let me shortly discuss what happens if we increase temperature. Well, I told you that the width of these peaks is determined by temperature. There are regions where energy to overcome Coulomb blockade is small, smaller than temperature. So if you increase temperature, no wonder if they become wider. And at some stage, they would rather merge. At temperatures of the order of Coulomb energy. Interesting point, this is not all what they do. If you increase temperature further, there will be a region, an interval of temperatures where this curve, although very smooth, you don't see much peaks, where the whole curve rises in conductance. Eventually that makes single electron transistor a good thermometer in this region that can be applied. How to explain this? It's important to recognize that for same junction, the difference between these two values of conductance is approximately 2, factor of 2. What happens is the following. Let me explain it at very qualitative terms. Let me look at the drop of this peak at low temperatures. Here we have transport, but still in Coulomb blockade regime. It means that electrons here go one by one, as we described. No second electron can eventually enter the island when first electron is present. So, what does it mean? It means that conductance is efficient only for half of electrons, as compared with the case where no restrictions are imposed. Which means that conductance is a half of maximum conductance available in this structure. Right? And when you go increasing temperature in this interval, you cross over between these two values of conductance. So it's crossover between the transport where double occupation is allowed, this level, and the level at which the electrons go one by one. Good, Coulomb oscillations. I will talk about another manifestation of Coulomb blockade. I will talk about Coulomb staircase. Coulomb staircase is seen in nonlinear transport, and it is based on the following phenomenon. Suppose you have a Coulomb blockade, no current, you increase voltage, then a process becomes open. Let me sketch the barrier. The diamond with 0 charge and with 1 charge. Right? Let us see. So we sit here, we increase voltage, we cross to this domain. Sorry, wrong color. And here in this domain, possible electron states is 0 and 1. No other electron transfers are allowed. Well, we can go further in voltage. And we cross the boundary of this extra diamond. Here we expect more states coming into play. What are states? 0, 1, and also -1 coming from this domain. Good. So if we increase voltage, we make more charge states available for transport, and that in principle gives a peculiarity, a cusp, a change of derivative at early curve. Well, that's kind of theory. Practice might be somehow different. If the conductances are the same, these cusps are present at periodical values of voltage, but you can hardly see them. So just visibility is very small for junctions of comparable conductance. But one can change it, making conductance of one of the junctions much bigger, much smaller than conductance of other one. Then Coulomb staircase becomes much more prominent. One doesn't even see cusps, one can see steps situated at voltages when, again, more charge states become available for tunneling. Another manifestation of Coulomb blockade, you take a device, you measure it. If you see those manifestations, you're sure that transport in the device is governed by Coulomb blockade. Another condition is that resistance is still low. Sorry, resistance is sufficiently big. It must provide enough isolation to keep discrete electrons to keep all these peculiarities of Coulomb blockade. Good. In the time remaining, let me talk about more complex process which can occur in Coulomb blockade structures. Somehow funny and I would say rather instructive process. The process is called co-tunneling or cooperative tunneling. This process becomes relevant when single electron tunneling is forbidden, is pressed. Right? For instance, in Coulomb blockade domain, in this case, an electron which would come here and the island would need to have energy which it cannot afford. Right? So it's forbidden, but it is something which is not forbidden fundamentally, and electrons, being tricky guys, they can find a way to circumvent this. In order to cheat energy conservation, they have to cooperate. Let us consider a process whereby one electron enters this island and simultaneously or very soon another electron goes out. So it's fine. There is no charge in the island in the final state. No problems with spare energy. But the electron transfer has happened. We have transferred one electron from the left lead to the right lead. This is one example of what in quantum physics are called compound processes. In this case, if we want to relate the rate of this process, we can use usual Fermi rule expression. The amplitude squared, matrix element squared, and okay, that guarantees that the energies of initial and final states are the same. The amplitude of this complex process is made from amplitudes of partial processes, electron tunnelings, and it also involves the energy difference between these two states. Let me give more details. In this case, we are saying that the process goes through virtual state, formerly forbidden state. One cannot be here because it contradicts to energy conservation. But one can visit this state for a short time and perform a jump to another state. Good. So, electrons will go through the virtual state, and this virtual state is a state with one extra electron in this eye. Why? Let me show a Lensy formula and let me explain what the elements of this formula mean. It describes co-tunneling of two electrons which goes through the left and right junctions. Do that together. So the rate through one junction is proportional to conductance, the rate through another junction is proportional to conductance as well. So altogether we have a rate which is proportional to the product of conductances. This rate involves electrons in with different energies. That's the energy of one electron on the left, energy of another electron on the lead. And there are energies of the states in the island they come from. All these states have to be free, all these states have to be occupied. So there is an energy difference between virtual states. It contains charge and energy. There are two virtual states, with plus charge and minus charge. And there's energy conservation as I described. So co-tunneling, being a complex process, still can be expressed through conductances, through charge and energy. What is the answer? The answer is that even at zero temperature, inside Coulomb diamond, there's still some electron transfer, still some current going in. The current is proportional to the product of conductances, measured in conductance quantum. So it's much smaller than the typical single electron tunneling. It also involves energy differences, energies to pay. And to coincide this, it's proportional, strangely enough, to the cube of the voltage. So there's a story about co-tunneling. Let me give the picture of what is going on when we, at a certain setting of gate voltage, increase applied voltage. So, single electron tunneling would be this red line. No current up to the threshold, and then, well, it increases linearly. You remember these rates which are proportional to energy difference. You increase a voltage, you increase this energy difference. Very good. Co-tunneling would be this green curve. But if I just look at the expression of the co-tunneling, it diverges at this threshold. What does it mean? Why does it diverge? In this case, cooperative tunneling of two electrons through left and right junction is not distinguishable from single electron process, when first electron goes to the right, to the left, and then to the right. So what happens here, the H is neither co-tunneling nor direct transmission. That's something in between. That describes the transition happens at the edge of Coulomb diamond. As you see, it is smoothed at finite conductances owing to tunneling, owing to quantum effect. Alright, this is what I wanted to tell you about Coulomb blockade. So it's quite different from scattering theory, which we considered in the first lectures. Surprisingly, the same quantity GQ governs Coulomb blockade as well. GQ sets the level of isolation when charge quantization is still visible. Charge quantization is important, survives only there are good barriers separating islands. Charge in the island is discrete. We understood how to compute energy using simple electrostatics, adding capacitive energies. We look at single electron transistor. It is described by master equation. One has to understand which rates are forbidden, which rates can be. If all rates are forbidden, we have Coulomb diamonds, regions of zero current. We can compute it for the currents combining master equation and expressions for tunnel rates. That will allow us to describe features, peculiarities of Coulomb blockade. Finally, we look a bit at more complex quantum processes which involve more electrons, which are called co-tunneling of electrons in Coulomb blockade circuits. Alright, thank you for your attention. That was an unusual lecture which I have to improvise, so it's not really good, I presume, but for the lack of better. I have to work to flip the image which I see now. It's now mirrored my camera. I hope I will be able to do this. Alright, I will see you, or at least you would see me, for the next lecture. Thank you for your attention, and let's brave strange circumstances which which we experience nowadays. Good luck to you.